Okay, hello everyone. Welcome to this video. In this video, we will be solving for 6 questions that have been provided for us. But before we start, let us first introduce ourselves. Starting from me, my name is Kenya Puenregata Sihaya with my student ID 2415101073 and my partner.
Okay, let me introduce myself. My name is Kadek Wahyu Ardia Putra with student ID 2415101002.
Okay, without further ado, let's start. Okay, I will start first. We will start with the first question here. So here, the question asks for us to prove that in order for us to check W is a subspace of a vector from this vector space, we only need to check the closure axioms. Now we also need to explain why we don't need to explain the other axioms. Okay, so to prove this, we actually need to make sure of 3 things. I'm going to write this down here. The first one is we need to make sure that W is not a null set. The second one, we need to know that if W has UV as a value in W, then it needs to be closed under addition. And we also need to know scalar multiplication, which is A is a scalar inside of a field, and V is a part of W, then it needs to apply that a scalar multiplication will still be inside of W. Okay. Now, because V is a vector space, each axiom, which is associative, commutative, distributive, and etc., has applied in V. W operation is only the limitation operation in V. Therefore, those axiom applies for each element in W, and we only need to make sure W is not empty and close in each operation. Now, let's start with the first one, which is proving that W is not a null set. Okay, here. W not a null set. Now let's take now use action with scalar 0 from the field. And just multiply that with W. It being like this. Now, therefore, vector 0 or 0v in V is also in W. Next, for each V, the elements of W with scalar -1 from field equals to -1V, which is equals to V that is still in W. This proves that W is a subspace because it has an inverse that is also in W. Now, what exactly does this mean? Let's talk about this in detail. Now, for each scalar in field, let's say we have A, and each vector, which is a small v with phi, AV should be a vector in V. Now this means the multiplication fuses one element in V with one element from a vector space, resulting in a result that comes back to the vector field. Now what does it relate to with the negatives? Now, if V is also part of W, that means A in F, then AV is also in W. This means it is close in multiplication, and multiplying it with a random scalar and vector in W will still equals in W. So here we see minus V included in W, so each vectors in V has an inverse in W. Now, what about the addition? In addition operation here, if W is a subspace of V, addition operation in W is the same with V. Because if U plus V in V is always defined in V, therefore the same thing can be said in W, making that U plus V is also defined in W. So what does that conclude to? Because it is already known that W is closed under addition, because W closed under addition and scalar multiplication, and each axioms are inherited from V. This means each axiom of vector space is also fulfilled in W. Because all of it is also fulfilled, we can say that W is a subspace of V. Now, that's for the first question. Let's move on to the second question. The second question asks for us to prove that each vector that are in a straight line in R3 will make a subspace vector from R3. So here's the thing. Not all lines in R3 is of subspace. Okay, only those that went through 0, 0, 0 can be considered as a subspace. Now, say that the line is a set like this. T, V, where T is an element of R. Okay, with V as a constant vector. Now, we have 3 points that we should make here. Now, if T is 0, then 0 times V will be equal to 0. This line goes through the origin point, which is the 0, 0, 0. Now, the second point, if we take 2 points like T1V plus T2V, and then make some operation like this, this is also still on the line. If we multiply it with a scalar, say that it's A, and it goes like this, it is also still in line, because all of this fulfills the 3 point that we have made on the first question there. Therefore, each line that passes the origin point fulfills the subspace condition. But if it is not passing the origin point, such as, let's say we have G, which is 1, 0, 0 plus T, 1, 1, 1, this is not a subspace because 0, 0, 0 is not present in the line. Pretty simple. Now let's go to the third one. Okay, the third questions request us to explain why a plane that went through a point, oh, I'm sorry. It asks us why a plane that went through an origin point in R3 has this equation right here, which is AX plus BY plus CZ equals to 0. I'm just going to write that down. AX plus BY plus CZ equals 0. So it's asking us why it has this equation right here with ABC is an element in R, and XYZ represents the coordinate point in R3. Is that plane a subspace of R3? Okay, so we can actually write this like this, where P is XYZ, an element in R3, where AX okay. So we have talked about point of origin, right? So point of origin, which is 0, 0, 0, fulfills this equation. Let's say we input this origin point into the equation like this. It will result like this, meaning that it fulfills and the plane is not an empty and passes the origin point. Now, even if we take 2 points in the plane, the result of the addition will still fulfill that exact equation. Now, let's say like this. U is x1, y1, z1, and v is x2, y2, z2, where u and v is an element of p, and n times u or n times v is equal to an ax0 plus x2 by2 plus c z2 equals 0. Okay, this operation we can actually write u plus v, which is the addition, x plus x2 y1 plus y2 z1 plus z2, and then we can take out the n like this, and u plus p equals a x1 x2 b y1 y2 c z1 z2. Now, because the left side is 0, we can say that n u plus v equals to 0. This proves that p is closed under addition. Now, let's take a random point, which is q. This is a random scalar from R. and u, x, y, z, which is still an element of P. Now, let's check. Q multiplied by U. We're checking for the scalar multiplication right here. Just multiply Q into XYZ like this. Oh, and then operate it with N. Again, do the same thing. Insert this all to the equation, which is A, B, C, which will look like this. Operate it. Just take out the Q and AX, BY, CZ equals to 0 times 0 equals to 0. Now, since n times q times u like this equals 0, we can say that qu is an element of P, making P is closed under scalar manipulation. Okay, so we have solved 3 questions here. I'm going to give the rest to my partner.
Okay, thank you, Kenya, to solve number 1 until number 3. And now, hello answer number 4 until number 6. Okay, the question number 4 is create a set S is vector U, vector V, and vector W consisting of 3 linearly independent vector in R3. Okay, for number 4, we choose the standard bus vector in R3 like is 1, 0, 0, V is 0, 1, 0, and W is 0, 0, 1. Okay, the first question is so that the system of linear equation K1U plus K2V plus K3W equals V0 has only one solution. One solution. Okay, the first step, we substitute the choose vector into the linear combination equation that equals to 0 vector. K1 times 1, 0, 0 plus K2 times 0, 1, 0, and then K3 times 0, 0, 1 equals V0. Okay, the next step we just calculate this equation. And if we calculate this equation, the answer like this. Plus 0 k2 0 plus 0 0 k3 to be equals to be 0. Okay, the final result is like this. Okay, for one question, the only solution this system linear equation is the trivial solution like k1 equals 0, k2 equals 0, and k3 equals 0. Since the only linear combination yielding the 0 factor is trivial 1, the set of U, V, and W is linear independent. Okay, now we jump to the question number 2. Okay, the question is this set a spanning set for R3? Okay, for the definition, a set S span R3 if every vector like Z equals Z2 and Z3 in R3 can be written as a linear combination of the vector in S. This is linear combination. Okay, can be written like this. And number 2, we just change the constanta to be Z. K1 times U plus K2 times V plus K3 times W equals to be Z. Okay, we just substitute the vector U, V, and W into this equation. Okay, we just calculate this equation again, and the result is, okay, this directly give a unique solution for the coefficient. Like K1 is Z1, K2 is Z2, and the last one, K3 is K3 equals Z3. Okay, since a unique solution for the scalar K1, K2, and K3 exists for any vector Z is an element of R3, the set S span R3. So the answer is yes, the set S span in R3. Okay, now we jump to third question. Okay, for third equation, does the set of vector resulting from the linear combination of vector U VW form a vector subspace of R3? Okay, to prove this question, let W equals span U V and W. Let W is span U, V, and W be the set of all possible linear combination. For W to be a subspace of R3, it must be satisfy three conditions. Okay, the first condition is the first condition is containment of the zero vector. Okay, in this condition, we know the K1, K2, and K3 equals 0. Okay, we just substitute into the equation, and the result is like this: 0u plus 0v plus 0w, and equals to be 0. Okay, since 0 can be expressed as a linear combination, and 0 is an element of vector w. Okay, the condition number 2, closure under vector addition. Okay, for this condition, we take two vector like A and B from vector W. Okay, the vector A is C1U plus C2V plus C3W. And then vector B is D1, D1U plus D2V and plus D3W. Okay, their sum is C1 plus D1U plus C2 plus D2V plus C3 plus D3W. Okay, since CA plus DI plus are new scalar and A plus B is a linear combination of U, V, W. So A plus B is an element of W. Okay, for the third condition is closure under scalar multiplication. Scalar multiplication. Okay, for this condition, we just take any vector A is the element of W and any scalar J is an element of R. Okay, we know in second condition, vector A is C1 U plus C2 V plus C3 W. We just multiply by K. Multiplied by K. Okay, the equation is Ka plus A equals K C1U plus C2V plus C3W, and the result is KC1U plus KC2V plus KC3W. Okay, since W satisfies all three conditions, it is a subspace in R3. Okay, now we jump to the number 5. Okay, the question of the number 5 is create a set S is UVW consisting of three linear dependent vectors in R3. And so K1U plus K2V plus K2W equals 0 has infinitely many solutions. What is the parametric representation of this solution? Okay, for number 5, to prove this question, we choose the vector U, like 1, 0, 0. V is 0, 1, 0. W is 0, 0, 1. Sorry, W is 1, 1, 0. Okay, for the first, we just set the linear combination equals to the 0 vector. Okay, the equation like this. Okay, this is the equation. Okay, now we just calculate this equation. And the equation like this. Okay, for this equation, we get the system linear equation like K1 plus K3 equals 0, K2 plus K3 equals 0, and then the last is 0 plus 0 equals 0. Okay, since the system has fewer equations, then variables, three variables like K1, K2, and K3, 3 must be a free variable, which leads to non-trivial solution. Okay, let K3 be the free parameter. K3 is a free parameter. Okay, we assume K3 is T, where T is real number. Okay, we know the K3 equals T. We just substitute K3 into this equation like, okay, for the first equation like this, k1 plus t equals 0, and we know k1 equals minus t. Okay, for the second question, k2 plus k3 equals 0. Sorry, k2 plus t equals 0. And we know the k2 is minus t. Okay, for the equation, k3 is t. Okay, we know k1 equals minus t, k2 is minus t, and k3 is t. For any t is a real number. It's a real number. Okay, now we just express as a factor of coefficient. And like this, k1, k2, k3 equals t minus 1, and 1. Okay, because the solution depend on the parameter t, which can be any real number, the system of linear equation has infinitely many non-trivial solution, and the existence of non-trivial solution confirm that the set S is U, V, and W is linear depend. Okay, for the number 6. Okay, the question of the number 6 is the set S that you form in question number 4. Question number 4, a basis for R3. Okay, we know in the number 4, the set S is 1, 0, 0, 0, 1, 0, and 0, 0, 1. Okay, according the formal definition, a set S is like V1, V2 until F VR is called a basis for a vector space F if the condition are, okay, this is the condition. Okay, the first condition, S must be linear independent, and second condition, S must span the space of V. Okay, in case of the number 4, the S is 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Okay, first we prove first condition. Condition. Okay, the condition number 1 is linear independent. Okay, to condition number 1, let's see this answer. Okay, as proven in number 4 sub 1, we know the k1, k2, and k3 equals 0. This is the homogeneous system of linear equation of k1 u plus k2 v plus k3 w equals to be 0, and only yields the trivial solution. Okay, for the condition number 2 is S must span the space V. Okay, for the two condition. Second condition, let's see number 4 sub 2. Okay, this is the proven second condition for number 6. Okay, in this answer, we know z equals z1, z2, and z3 is the element of R3 can be uniquely written as the linear combination like z equals z1u plus z2v plus z3w. Thus, S span R3. Okay, in this answer of number 4 sub 2, we know the K1 equals Z1, K2 equals Z2, and K3 equals Z3. And this equation we just substitute into this equation. And the final equation like this. Okay, since both conditions are satisfied, the set S, the set S like 1, 0, 0, 0, 1, 0, and then 0, 0, 1 is a basis for R3. Okay, we have done to solve number 1 until number 6. And maybe that's all from me and that's all from our presentation. And we close with thank you everyone.